Okay, Mr. Sonnenberg here. We're doing Science 7, the unit heat and temperature. We're in General Outcome 2, and I'll let you read what it's about. But basically, we're looking at the nature of thermal energy and its effects on different forms of matter using informal observations, experimental evidence, and models. So, which we'll do when we get to more of our B-layer activities, and we're completing more lab-based activities as well. But right now, today, we're talking about specific outcome 2.3. So we're describing the effect of heat on the motion of particles, and we're explaining changes of state using the particle model of matter. Now, this particle model of matter, which we've already discussed a little bit, is something that's going to follow you around throughout your science courses. It's going to keep coming up, and so if we become really familiar with it as a grade 7 student, then when we come to grade 8, we're going to notice, oh, there's that particle model of matter again, and when we get to grade 9, oh, there's the particle model, and then through high school, it's going to keep coming up as well. So it's good. It'd be important, I would say, for us to understand what the particle model of matter is. So first, we're going to talk about heat capacity and specific heat capacity. So basically, if I take a chunk of ice and I increase and I add thermal energy to it or heat energy, and so I take the heat of the sun and I put some ice outside on a hot day, it's going to melt. So what we're looking at with heat capacity is what is the capacity at which it can handle the heat before it changes states. So this is different materials will increase or decrease their average energy depending on how much thermal energy is provided. So if we provide more energy, the energy of these materials may increase or decrease. So sometimes they will absorb energy, sometimes they will release energy. Okay. So heat capacity is the amount of thermal energy that warms or cools an object by 1 degree Celsius. So what does it take for an object to either become colder and cool itself by 1 degree Celsius, or become warmer and increase? So what we'll do is throughout this lesson is we will look at, I like to use water as a good example because it changes states easily. So this heat capacity depends on the mass and the type of the particle the object is made of. So how heavy is it? How much of the material? If I had ice, how much do I have? Obviously, if I have a big chunk of ice and a small ice cube, and I apply the same amount of thermal energy, and I'm going to warm it, well, one is going to warm up at a faster rate than the other. And it describes a particular object. Specific heat capacity, on the other part, is now the word specific. Obviously, we're narrowing it down. We're looking at, instead of just the amount that it takes to warm or cool an object, now what we're doing, we're looking at the amount of thermal energy that warms or cools 1 gram of a specific type of particle by 1 degree Celsius. So it depends on the material of what the material of the object is made of. So we're looking at 1 gram. So we don't worry about the mass anymore because we know it's going to equal 1 gram. And that's what we're looking at, specific heat capacity. How does 1 gram of this specific type of particle, how much energy does it need, thermal energy does it need to increase or decrease it by 1 degree Celsius? Okay, so we're describing a particular material here, okay? And like I said, all it does is it depends on the material the object is made of, okay? So whereas heat capacity was discussing what's the mass and what is this object, what are the particles like, what is it made of? So that's heat capacity. So we have to understand that if we increase or decrease the temperature, different materials and particles are going to react differently. But how do we increase and decrease the temperature? By warming and cooling 1 degree Celsius. So what is, we could calculate, we can look at what is the low specific heat capacity, the high specific heat capacity, and And as we get to our B layer activities, we'll be doing an activity that's going to help us to better understand this by analyzing and interpreting this concept. So when I talk about the particle model of matter, what I'm talking about is how the particles react, and then also how particles are, how they're arranged. So we know there's three states of matter that we're going to cover today. There's the solid, liquid, and gas. Solid right here, their particles are closely packed together, where the liquid, they start to move farther apart. Now, these particles are always in motion. A solid you would look at and say, well, it doesn't move. Well, the particles are still moving, they're vibrating inside. They're just very small spaces between them, and so their arrangement is closely packed together. Whereas a liquid is slightly farther apart, and the particles are more in motion and moving slightly faster, but liquids have the ability to flow. So again, like I said, we're going to use the example of water in its three states. And then if we look at gas, or what we'll call water vapor, is what's happening here is the particles are even farther apart, moving more rapidly and moving more freely, and so we have a gaseous state. So we're going to talk about how these changes of state occur and what each are called briefly here. So we start with the solid, so we're going to call that ice. Solid water, we're going to call it ice. We're going to add thermal energy, okay? So we're going to add heat to the snowman. Now what's going to happen is by adding heat, the particles are going to spread out and become farther apart and move a little faster, and it's going to turn into liquid water. Okay, so now we have this liquid water. Well, if we increase the thermal energy again, or the temperature, what we're going to get is a process of evaporation, and then that is going to turn this liquid water into what we call water vapor. Okay, so now how do I turn this water vapor back into water? And so this is somewhat similar to the water cycle when we discussed it as well. So how do I turn this water vapor back into a liquid? Well, the process is called condensation, and what's going to happen is now I'm going to cool the temperature of the water vapor, and I'm going to cool the particles, which is going to force these particles that are farther apart, moving rapidly, to slow down slightly and become slightly closer together, and they're going to form water droplets, which we call condensation, and now they're going to form back into liquid water. Now if I cool this yet again, this liquid water, think about right now in the Canadian winters, what happened to all the lakes, the top layer of the water in the lakes? Well, it froze. So now if I cool this liquid water to its freezing point, I'm going to get this process called freezing, and I'm going to turn it back into solid ice. Now if I was to take this solid, there's a process we call sublimation, and go on both ways from a solid, and then it turns into a gas or water vapor right from a solid, or from a water vapor directly into a gas. We call that sublimation. Okay, so those are the three states, and so it's important we understand how if we increase the temperature, the thermal energy, we can in fact change the state of a material. And the particles are again closely packed together, with the solid slightly farther apart, moving more rapidly in a liquid, and then again moving the fastest and the farthest apart in a gas. So changes of state. So if we look at water, for example, it can undergo observable changes through the three states: solid, liquid, and gas. Some substances, so we'll look at hydrogen, it requires pressure and low temperatures, minus 250 degrees Celsius or 253 degrees Celsius, to make particles slow down enough for them to change their state from gas to a liquid. So it reacts quite differently than water. So I just have it bolded that any pure substance can exist in all three states of matter. Melting and boiling points. So when heat is transferred in a space, the average energy of the particles, so which is the temperature of the substance, is affected by increasing or decreasing. The substance will change its state when it reaches certain temperatures, and this is called the boiling and melting points. Okay, so melting and boiling, obviously, if we look at water, well, in order for uh, water to melt, we have to be over 0 degrees Celsius, right? Because it freezes at 0 degrees. And for it to boil, we reach 100 degrees Celsius. So what happens when, let's look at evaporation, but when this liquid evaporates, so if I put water on a countertop and I left it at the end of the school day and then I showed up again, that water would probably be gone in the morning if it was a small amount. What happens there? Where do the what happens when this liquid evaporates? So in these fluids, the particles are moving very quickly. Okay, in these liquids. So at the surface, if we take a look here, at the surface, some of the particles are able to escape into the air. So while others do not have the energy to escape and remain in the liquid. So some have more energy and then they can escape. And the particles move fast enough that they turn into a gas and they evaporate. And others have to stay there for a longer duration of time. Same thing when we look over at the coffee. Some of these particles are escaping while others are remaining in the coffee itself, right? Because we've increased the temperature. Oops. Okay. So as the high energy particles escape, the average energy of the remaining particles is less, and so the liquid cools. So we have these particles that are gaining energy from the heat. And so what they're going to do is then they're going to escape and they're going to turn into a gas because the particles are moving fast enough that they change state. Now, the other one, so without this heat or with this high energy, the rest of the coffee or the substance is cooled. So if we look at the coffee, well, it's evaporating, there's heat loss, and therefore it's left with some lower level energy, and the liquid then begins to cool. So the cool liquid, it cools the surface of which it's resting. So that process is called evaporative cooling. Okay, so where we can actually cool that surface, examples of this would be a jogger cooling down as their sweaty clothes dry out. Okay, or water cooling down a roof on a hot summer day, or a wet cloth placed on your forehead when you have a fever. That's actually going to cool us while the liquid's evaporating, because we're taking away that high energy particles and we're forcing them to move away, and we're actually replacing them with lower energy particles that are going to cool us. Okay. So why does temperature stay the same? So during a phase change, the average energy of the particles, or the temperature, remains the same, but the particles are rearranging themselves. So the particles become less organized as their energy increases. So the substance changes from a solid to a liquid to a gas. So a solid state would be the most organized particles, and then the liquid would be moderately organized, and then the least organized would be a gas. And like I said, particles are closely packed together, therefore they're more organized than a solid. As we increase thermal energy, change the state to a liquid, what happens is the particles are less organized, they're farther apart. Now the substance has the ability to flow in a liquid state, and in a gas it also has the ability to flow, but the particles are farther apart and moving more rapidly. So as the energy of the particles becomes less, the particles rearrange themselves more orderly. So a gas changes to a liquid and then to a solid. So now we have the opposite direction happening. So The temperature is the same, but the particles become more organized as the the particles become more organized. So if we take that energy and there's less energy in the particles, then what they're going to do is they're going to begin to arrange themselves more orderly. So the less energy they have, the state would become a solid. The more energy they have, the state would be liquid or gas, because now the more energy is causing the particles to move more rapidly. So we're talking particle model of matter. We're talking how do the particles react to heat and temperature. Okay, so an increase in thermal energy. So we're looking at this energy. The less energy we have in the particles, the more arranged they are and the more orderly they are. So the particles are packed closely together like a solid. The more energy we have, then we're looking at the less orderly and arranged they become, and that's the liquid and the gas. Okay. So the total energy of particles changes by increasing or decreasing, because the particles are not increasing or decreasing their speed, just their arrangement. Okay, so they're arranged less orderly. Okay, and so what's happening is that's the total energy changes based on this arrangement of the particles. Okay, becoming farther apart. Okay, and so the average energy or the temperature doesn't change. So the particles themselves aren't changing, they're just rearranging themselves in a more or less orderly fashion, and the temperature is remaining the same. So I put some sources up here. One is just some information is taken from EdQuest, and two, there's a YouTube video actually. It's pretty interesting. It's a song on the force state changes in the matter. It talks about plasmas as well. We just discussed three states of matter and the changes in that, but you can watch the video and view it again on this site, and if you go down to descriptions, I'll have a copy of that video actually added there as well. And so hopefully this helps. You can play, pause, and record, and hopefully this helps you a little bit or quite a bit as we move through the lessons. Alright, thank you for viewing.